guys, welcome to your notes for section 4.4. I am so sad not to be with you today because today is such a fun and important day. It is the fundamental theorem of calculus. This is the shortcuts you've been waiting for finding the area underneath your curve. So in the last set of notes where we talked about that limit definition for definite integrals, we did define sort of the notation. We talked about how we can set up basically our antiderivative. We can talk about the integral of a function. And we mentioned how we can attach these boundaries. And when I write it like this, I'm actually not just saying find me the antiderivative, I'm saying compute the area underneath the curve f of x, starting at a and ending at b. There are a couple of stipulations, but we're not ever going to run into anything tricky in AB. We do need to assume the function is continuous. You can't have an asymptote or a jump right in the middle. And your antiderivative does have to exist. So assuming that you can integrate f of x, we would say that we would have our antiderivative. And here's the trick. We're going to plug in our b value, our upper bound, to that antiderivative, and then subtract the antiderivative evaluated at a. So the integral from a to b of f of x dx is equal to f of b minus f of a. I'll show you some examples. It'll go pretty easy. If you can find the antiderivative, you can compute the area. We just talked about that. When applying, we typically do this first. We would say, all right, well, I'm going to take the antiderivative of my function, and then we use this notation. We can put a bracket here, and we'll transfer over our bounds. This is just a really nice way of saying, look, Mrs. Bragg, I know how to take the antiderivative. I can show you that work. Now I'm going to go ahead and apply that fundamental theorem, and I'll evaluate that antiderivative at b, I'll evaluate at a, and I'll subtract their difference. So let's start out with a really nice and simple example. Here we are talking about the integral of x to the fourth from 1 to 3. Really, visually, if we were to graph x to the fourth, what we're doing with this computation is we are calculating the area underneath the curve x to the fourth, so below the curve above the x-axis, starting at 1 and ending at 3. If you remember from, before the semester started here, the power rule for polynomials, we're going to add to our power, so x to the fifth, divide by that new power, and then our notation, we're going to put that bracket, and we'll keep the 1 and the 3. So we're just taking a moment to say, yep, I know the antiderivative. Notice we leave off the plus c's. When we're doing an indefinite integral, when you don't have the bounds and you are just plugging in the values here, you don't need them. When you have no bounds, you do need the plus c. It's a different kind of question. The rest of this problem would look like this. We'd take our top number and we would plug it in. And then we'll subtract whatever we get when we plug in the bottom number. 3 to the fifth happens to be 343. Whoops, I didn't mean to put an equals there. We want to subtract our 1 to the fifth over 5. So for a grand total of 342 over 5. And you know what? I messed up. I had 3's in my head. Sorry about that. Maybe some of you caught it. 243 and 242. So that's how it works. If you could do 4.1, you can handle this. You're just plugging in some numbers. Like I mentioned, we do not need to include it. Let's imagine that we did. We took our antiderivative, we included the plus c. That would mean that when I plug in the top value, right, I would have f of b, but the constant wouldn't be affected by the b value. I would immediately be subtracting f of a plus c, but what happens when you have that constant and you subtract the same constant? They would zero out. So the convention with the definite integral, where you have the bounds on the integral symbol, is to completely just ignore the plus c's. When you do not have bounds, you must include them. So you don't want to forget your plus c's on. Let's try a few. Let's see, the integral from 1 to 2 of x squared plus 1. The first step is just antiderivatives, just like we did in the earlier section, 4.1. You can flip back to your notes. We would write this as x cubed over 3, right? I added 1 to 2 and divided by that new power. And then the integral of 1 would be x, right? The derivative of x is 1. I make my little notation that this is a definite integral, so I want to go ahead and plug in my 2 first. We'll take and we'll have, let's see, 2 cubed, that makes 8 over 3 plus 2. I tend to put it sort of in a group and say, well, this is what I got when I plugged in the first number. And then I'll subtract, it's always a subtraction, and then I'll plug in the bottom. So 1/3 plus 1. So if I had 8/3 and I subtract 1/3, that's 7/3. 2 minus 1 is positive 1. And let's see, this gives me 10/3. It does here say use your graphing calculator to verify your answers. And I want to take a minute just to show you how that works. In this chapter, we will not be using our calculators. You'll need to show all your work. But eventually, when we move into applications, we will only use our calculator. All of our work will go into the setup, and we'll just use our calculator to finish the computation. So it's definitely worth talking about. There's 2 ways to go ahead and do this. So the cool way, I think, visually, you can see what you're doing, is to go ahead into your y equals menu and type in your function. So that integrand would be x squared plus 1. And I'm going to just double check my zoom here and graph it out, right? It's what I would expect, my parabola. In the calculate menu, so second trace pulls up the calculate menu. Look down here at number 7. That's what we want to go with. So we're going to choose number 7. And this lower limit, these are your bounds. Don't use the arrow keys. They're not accurate enough. You can actually just type them in. So I'm going to put a 1 in for my lower bound. Press enter. The upper bound would be the top number, so 2. And I'll press enter again. And look, it even goes ahead and it will shade it in for you to sort of show you what it's representing. Maybe you already recognize that 10/3 is 3.33. Cool trick. This is the last answer that you computed. If you went to math and then pressed enter for the fraction, it'll actually take and compute it to that nice exact fraction for you. So you can check your work that way. Another way to do it, you can do it all in the screen right here, in your home screen. If you don't care about the visual, go ahead and press math. And, oh, I gotta remember where it's at. We are still in that math heading. I didn't move over, but I'm in option number 9. Looks like function integrate or something like that. And I can choose that. It pops up just like your textbook is written here. So we've got from 1 to 2. I just use the arrow keys to move in between x squared plus 1. You do have to tell it the variable. So whatever letter that you're using here inside your function should match over here. So I can just use x. I always use x no matter what it is because it's easy to press. Your calculator doesn't know the name. And again, you can compute it that way. So if you're not interested in the image, you can do it all on your home screen. So for right now, you can use this to check your work. Just know that on the test, I would expect to see all of your work, or maybe you wouldn't have a graphing calculator to work with. So here's another one, just a review mostly of our integration. Right? This is saying, find me the area underneath the curve 3 roots of x, starting at 1, ending at 4. We talked about how to solve these back in 4.1. It's easier to look at it as a power, right? And then I would integrate first. So I'll take 3. If I add 1 to a half, I'll have 3 halves. Instead of dividing by 3 halves, I want to multiply by 2/3, just a little cleaner. And this time, because I have bounds on my integral, I'm going to skip the plus c, and I'll keep my bounds instead. All right, so a quick simplification. You've got 2x to the 3 halves, evaluated at 4 and 1. So this would be 4 to the 3 halves minus 2 times 1 to the 3 halves. Quick trick, right? You don't have to cube it first and then take the square root. You can take the square root first. 4 to the 1/2 is 2, and then 2 cubed is 8. So 2 times 8 gives me 16. And this one's easier, 1, right? So 16 minus 2, I should be getting a 14. And I'll let you take a minute to put it in your calculator and you can try it out. Let's see, secant squared. Hopefully this is one that you have memorized, right? What function gives you secant squared as its derivative? That would be the tangent of x. And because I have a definite integral, I leave them hanging around on that bracket. So here I'm going to plug in the top Tangent of pi over 4 minus the tangent of 0. Use your unit circle knowledge. Tangent of pi over 4 is 1. Tangent of 0 would be sine over cosine. Sine of 0 is 0 over 1, so we get a 0. And the area underneath that secant squared curve is exactly 1. See if you can figure out how to put this one in your calculator. You've got to do 1 over cosine squared, but it's a little tricky to type in. Might be worth a minute to see if you can figure it out. We'll flip it over, and we'll try a couple more. I'm actually going to skip to the bottom of the page first. It's more related to what we've been doing, and then I'll come back and we'll deal with absolute values separately. So find the area of the region bounded by this graph, the x-axis and the vertical lines. Notice here, unlike the other three, they didn't set it up for you. So your job is to figure out sort of, what are the bounds? What function am I under? That kind of thing. What I did here, in order to graph it, imagine I stole your calculator, right? I went ahead and I factored out a -1. So that's x squared minus 2x minus 3. And that allowed me to find my intercepts, right? I would have a -3 and a +1. So the graph of this thing, right, is going to have zeros at -1 and at +3. It's an upside down parabola. You could find the vertex if you wanted, although it's not super important. Let's see, it would be -b over 2a. So let's see, actually -2 over -1 times 2, -2. So it's at 1. And if I plug in a 1, I'll get 5. 5 minus 1 is 4. 1, 2, 3, 4. So there's my sketch. Oops, I missed. Make our point bigger. So this is part of my fence line for my region. The x-axis is the boundary line, and the vertical lines x equals 0, it's the y-axis, and x equals 3, although it only hits at a point here. The area that they are trying to describe, and it's worth your time to make sure that you understand why, is this piece right here. Right? I don't have a geometric formula for that. So I am going to set this up as the area is equal to the integral. Where do I want my region to start? Where do I want it to stop? Well, I would start, if you think about Riemann sums, I would start drawing rectangles at 0, and my region ends when x is 3. And I want to come up with the area underneath that curve, 3 plus 2x minus x squared. And the dx really does need to be there. It just, finishes off the correct notation. And so I can use that summation property for integrals, right? I would get 3x plus, let's see, it would be x squared over 2, so x squared, the 2's would cancel, and minus x cubed over 3. That's my antiderivative. I want to drag around those boundaries and say, well, I still need to plug in my 0 and 3. So overall, right, if I plug in 3, 3 times 3 makes 9, 3 squared is 9, 27 over 3 is 9. Oops, I should have put a minus there. So minus 9. And you will come to enjoy plugging in zeros, right? So 9 minus 9, this comes out to be a total area of exactly 9. I'm going to skip back up to our absolute values. We end up having a lot of applications that involve absolute value functions. We'll get to that in the last day that we do notes for this particular section. But in the meantime, I do want to talk about them. For part A, it's actually easier maybe just to do some geometry. If you can sketch this graph, right? Imagine that you wanted to find sort of the vertex of that absolute value function, right? Where does that thing equal to 0, right? Normally, for the absolute value of x, there's a turn at x equals 0. So where does 2x minus 3 equal to 0? That's going to happen at 3 halves. So 1, 2, 3, 1.5 would be right about here. And if I plugged in a 0, right, I get -3, but it's absolute value, so +3. And I could use symmetry and plot my next point over here. And so I can sketch out this graph. If I'm talking about the area, or the integral from 0 to 3, then I'm saying I want the area underneath the curve, starting at 0 and ending at 3. There are so many ways to do this question. Okay, you can integrate from 0 to 3/2 and talk about this as a linear function. Now this side would actually be negative 2x plus 3. You'd have to recognize how to set that up. You could calculate one of the 2/2 because of symmetry here and double it. Or honestly, there's no rule that says you can't use geometry where applicable, of course. So here, I went ahead and I just found the area of one of those two triangles, right? The base of that triangle is 3/2 and the height is 3. So the area of one of the triangles would be 9/4, right? This would be area A, and because of symmetry, you have 2A. So 2 times 9/4 is giving me 9/2. So we don't have to make it more complicated and use our integral techniques. If we understand what this is asking, we can by all means use a much easier method. Okay, so what does that look like with a harder function? Let's talk about what this particular function will look like. This function, let's see, if I wanted to graph it, x squared minus 4x plus 3 would factor. I would have x minus 3 times x minus 1. So the graph of this function has zeros at 1 and 3. And let's see, at 0, I would be up at 3. Right in the middle of those would be at 2, so 4 minus 8 plus 3. I'm right about here at 2, negative 1. And at 3, I'm back up here. So the area, I'm going through here and here. I'm not sure what I put that dot there for. It doesn't belong there. Right, and it would go all the way to 4. So the area that I'm interested in would be all of this. But here's the deal. I forgot, right, that this is the absolute value. This would be the area underneath that curve. Let's talk about what this would look like for the absolute value function. What's going to happen to a value that's down here below the x-axis? Well, when I throw the absolute value on the outside, that part is going to reflect up into the positive territory, right? At 2, instead of being negative 1, I would be at positive 1. And likewise, all these points here would pop up. So the area would be right about here. Now, unfortunately, we don't have a method of dealing with the integral of an absolute value. The only way to do it is to figure out where those turns happen. So we can set up our area. We're going to need quite a bit of space here. We're going to set up our area as the integral, and we're going to break it into parts. Starting at 0 and ending at 1, right? It really didn't matter that I had an absolute value in the first place, right? That part of the curve was already above the x-axis, so we'll have x squared minus 4x plus 3 times dx. That we'll call A1. And I can go ahead and compute that one out, right? This would be x cubed over 3 minus, let's see, x squared over 2. So we'll have a 2 here with the 4, and plus 3 times x, evaluated at 0 and 1. This comes out to be a third, right? Minus 2 plus 3. So 1 and a third is 4/3. You could probably make an argument a little bit about symmetry here. And you could also compute this last piece, right? A3 would be the integral from 3 to 4. And again, the absolute value function is really not affecting that computation, right? Because you're getting a positive number anyways for your y value. The absolute value does not affect or change that. So you would still have x cubed over 3 minus 2x squared plus 3x, this time evaluating at 3 or 4. maybe you instead talked about the symmetry of this particular function and just wrote equals 4/3. That would be fine too. Or you can plug in your 4s and you can get your answer, right? 4 to the third, that's 64 thirds. 4 squared, that's 16, so minus 32. And 3 times 4 makes 12. And then I would still have to subtract, right? When I plug in 3, I'm getting 27 over 3, so that's 9. 3 squared is 9 times 2 is 18. And 3 times 3 plus 9. So let's see, 9 and 9, actually this one zeroes out, right? It's going to disappear because I have 18 minus 18. Here, let's see, I've got 64 thirds and minus 20. So 64 minus 60 thirds, that's going to be 4 thirds as well, which is what we were expecting with our symmetry. Now, I skipped over the middle, right? This troublesome spot right in the center here is a little bit different. Right? Area 2 would be the integral, starting at 1 and ending at 3. But this time, right, I was actually computing negative numbers, and when I flip them upside down, I'm multiplying my function by a -1. So when you have an absolute value piece that is being affected, that is negative territory and therefore is reflecting upwards, you just multiply your function by a -1, and that would give you the curve that would describe sort of that flipped piece, that reflected portion. And I can go ahead, and really the math is not much different, right? There's just a negative sign in front of each of those extra pieces. So instead of having minus 2x squared, I'll have plus 2x squared. Instead of having 3x, I'll have a minus 3x. It'll change my signs, and I'll be evaluating at 1 and 3. Now, if you're crafty, right, you actually already plugged in the 3 over here, so you already know that when you plug in 3, you're going to get that 0. If you don't believe me, you can check it again. And then you're going to subtract, because with the definite integrals, you always subtract in between, right? When I plug in 1, I would get -1/3. I would get 2 and minus 3. So it's actually the same as what I had up here, but everything is opposite. So it's -4/3. I'm subtracting it, and so I'm getting +4/3. So the overall area, right, was 4/3, 4/3, and 4/3. So 3 times 4/3, which is 4. Cool calculator trick, just in case you were curious. Maybe you want to check your work on something like this, or maybe when we get to the applications, you'll be allowed to use your calculator. There is an absolute value function available. So if I wanted to look at this, I could type in my function, x squared minus 4x plus 3. You know what I forgot to do? I forgot absolute values. So let's hit math. That's where absolute value is hiding. And it's actually in the number column. So absolute value here, it'll glue in those nice absolute value symbols. And now I'll type in my function, 4x plus 3. And I can double check my graph. See how I did? See how it's got that little hump there? Well, that's where it was reflected upside down. And I can calculate option number 7. And I just want to tell it to start at 0 and end at 4. And there you go. I know that I can check it and I did it right. Work through the absolute values. This one's kind of a pain here because of all the 3 parts, but try one out because, like I said, you're going to need them when we move into the application piece. You should be able to do them without a calculator and not just with. So practice the graphing, practice the computations. Otherwise, the rest of the hour is yours to work on the assignment at the bottom of the page. It's from your textbook. Keep up the good work and use your time wisely. Thanks.